So there's a comment that will lead us on to the next topic I want to talk about. I want to hear about some of the new tools that you guys are developing and kind of where you want to look and how that determines how you're going to look. So this comment was from Hobbs555. I guess if there is life on Mars, it's deep underground? Is that how you guys see it too?
It's a good guess.
Yeah. Does that drive what you're working on?
Yep, indeed.
Future?
If anything we've learned about Mars is that the surface is extreme, but maybe as you get deeper and deeper, conditions become better and better. And so, and there are good reasons for it. As you get closer to the center of the planet, temperatures go up, and we know there's plenty of ice buried down underground. So at some point, theoretically, that ice should melt.
Yes.
Create maybe a habitable environment.
Yeah.
As you go deeper, also, some of the nasty things you get on the surface, you don't get at depth, like radiation. And so it's, as you go deeper, you're more protected from these things. So it's a good bet if you go deeper.
Okay.
It's also harder.
Yes. Getting.
So is that something you're working on, like how to go deeper?
We are.
Yes, yeah.
We ask, and then now the ball is on their court to come up with ways to do it.
I see. So you roll up at Michael's office.
Yes, I said, Michael, get me 2 kilometers, and then,
2 kilometers
and I'll
down.
come back 10 years later.
I'm going to need a lot more breaths.
Right.
Yeah. So we're actually we're developing a smart drill right now.
Smart drill.
Yes. Yeah.
Okay.
And so we want a smart drill because, again,
What does that mean?
well, it's a drill that deals with the problems it encounters, so we don't have to.
Okay.
And so all these robots, they're far away. It takes, on Mars, it takes about 20 minutes to get signal back, right? Okay. So you can have encountered a problem before the drill can have encountered a problem before we even know that it's going on. Okay. And it could be too late at that juncture if it just keeps trying to just drill as if everything was normal. So the smart drill tries to recognize problems and then fix them by, basically by trying to feel how it's behaving. So if you're drilling at home, you're putting a screw into a piece of wood. If something goes wrong, you can feel the drill shakes, or it hits a knot and it just starts skipping, or you thread the screw, or you strip the head of the screw. You feel that it's not right. Yeah. We can do similar things with our drill. We can look at vibrations. We can look at how much power it's drawing to do the drilling. We can look at the temperature, how hot it's getting, and we can use that to then try and decide, okay, this is a particular kind of fault, and there's several different kinds of things that can go wrong with drilling, and then we take particular actions to fix those problems. And so it can be things like there's a rock between the drill and the hole that it's drilling, and it just sort of binds up. Or there can be soil falling in, and it can't clear the hole fast enough, so it's not making progress. So yes, we instrument the drill, put lots of sensors on it, look at what data is coming back, and say, okay, this is a binding fault. This is we've hit a hard surface we can't penetrate. Here, take the appropriate action.
Yeah.
So the drill itself can actually figure that out on its own now? Is that what your goal is?
That's the idea, yeah. Okay. We've been teaching it to be a smarter drill.
The problem is that Skype calls between Mars and Earth are really, really bad. It takes about 20 minutes to get a hello back.
Wow.
And so we cannot rely on instruments there.
Exactly, and especially if we're drilling into like icy surfaces, right? We could conceivably melt the walls, and again, creating water, which is a planetary protection problem, but it could also possibly refreeze and get the drill stuck in the ice indefinitely, and that would be the end of the mission.
And that drill cannot wait for us to learn about it, decide what to do next, send the information. By then, it might be too late.
Right.
I can imagine trying to have a conversation with you, and 20 minutes later, I get a response back.
Imagine that.
Hello, Abby.
Right. And if you're asking for instructions, or Abby, I messed up, my drill is stuck. What do I do?
And you might only get 2 chances in the day to say something, which is actually the case on Mars. So
that really underscores the need for some kind of autonomy here, right? It's got to act on its own a little bit. Yeah.
Diagnose its own symptoms, right? And
precisely.
So you've said it can back itself out, or it can hammer through a hard thing, right?
So the drill we're developing is a rotary percussive drill, and so that means it can drill in like a normal drill, or it can start hammering to break up whatever it's drilling through to make it easier to make further progress with the more standard drilling approach.
Cool, man.
Yeah. Wow.
Sounds good. I'll take one.
So we have sent drills to Mars before, though, right? Can you tell us a little bit about?
Yeah. So Curiosity actually has a drill. It's similar. It's a rotary percussive mechanism, and I have here this. This is just a drill that I took from our machine shop. So this is not to scale. It's not an accurate representation of what MSL has. Curiosity.
Yeah.
So Curiosity's drill is a little bit fatter. and it's gets about a 5-centimeter depth, so something about this length.
We actually have video of it drilling
Yes.
that we could watch right now. On Mars, Curiosity is going to put down its drill.
That's the arm with the drill, yeah.
Yeah.
And this whole drilling process takes about 25 minutes.
Okay.
Right? And again, it takes 20 minutes
Wow.
for the start of the drilling to get back to Earth. Right?
Oh, okay, yeah.
So it's almost done by the time we'd find out it's begun.
Okay.
So if something goes wrong,
At the start, you're way too late. Yeah.
exactly.
So it's sped up right now.
Yes.
Yeah,
right?
that'd be
And it's also
sped
on a loop, right? So
Yeah.
we're seeing
Yeah,
it.
yeah.
Right. That's a slow process, though. I see.
Yeah.
It's not like my.
Meticulous.
It's
Meticulous.
meticulous. Yes.
That's the
Pardon
right
me,
word.
Curiosity. Okay, so it's drilling into Martian rocks. We have photos also of holes that it's drilled, which is kind of fun because it's on another planet and it looks just like a drill hole at home. Can we see the image of a hole drilled by Curiosity? Yeah, look at that.
Yeah. So the big hole is the drill hole. And then that gray material is the stuff that was cleared out of the hole as it was making progress. And then there's that row of little holes. That's where the laser zapped it to sort of vaporize what's there
wow.
and see what the rock is made of.
So I have a question. Why is it gray? Why is that powder gray?
We run out of paint.
Yeah. so Mars is known as the red planet, but it's covered in rust, oxidized materials. That's why it's red.
Okay.
But it's not red all the way through.
What?
And that gives you a good idea of why it's important to go deep, is because it's the depth dimension is another world.
Yeah.
We would have never learned that if we hadn't gone with
yeah.
it. Imagine what we can do if we go even deeper.
Right.
We might learn things
Right,
that
right.
were completely unexpected. That was unexpected.
So Curiosity taught us that it's not really a red planet.
Not inside.
Not in its heart.
Not in its heart.
Oh, planet.
Not inside.
I
That's
had no
right.
idea before I saw that photo.
It's pretty
I
cool.
seriously didn't know.
And it might be red in other places.
Yeah.
So if anything we've learned about Mars is that it's very different. It's
yeah.
not the uniform planet once we thought it was.
Which is why the rover robots are so important, right?
Yep.
We can't just characterize one little
spot.
region.
Oh yeah,
That's right.
right.
We need to move
Yeah.
around.
Maybe you land in the one spot that is gray
Right.
underneath.
Yeah, I
or
mean, imagine if
whatever
we
it
were
can
like,
tell you.
10 feet over from where life was.
Yes, yes, yes.
Imagine.
So we've looked at the Curiosity drill. You've shown us how big that is. What are you working on now?
Oh, yes. This is the drill that we're working on. It's slightly bigger.
It's a little bigger.
A little bit bigger, yeah. So what you see here is these ridges here, it's the flutes, and this is what lifts the material out of the hole.
Okay.
Right? And so we drill this, it's about 3 feet long, and then what we really care about is this last 10-centimeter bite here at the bottom, and you'll notice that the flutes are much more tightly spaced.
That's flutes.
Yes, yeah, the ridges, the ramp, right? Because this is it's a ramp. It pushes things up and goes out the top of the hole.
Right.
So again, they're denser here because we don't want the material to move by too quickly once we've hit the depth we care about, and then we pull this out of the hole up to a sample collection device, which then takes the soil to the instruments.
Gotcha.
For analysis. Yep.
And then we look to see.
And then we look for things like microbes or
Yeah.
organic compounds and things like this.
So what is this hole here? I'm looking down a hole right there.
Yeah, so there's a hole in the bottom, and that's for cables to go down, because again, this is a smart drill, and smart means sensors. And so
Okay.
we have in this drill, we'll have a temperature sensor to see how hot it's getting, because that tells you like how hard is it to drill into to what you're drilling to. And then it also has a conductivity sensor, and
What does conductivity mean?
that'll help us detect if we hit water or ice
Yeah, or
in the hole.
or we're making liquid water.
Yeah.
If there's liquid water, it's going to send a signal. If it's dry, no signal. So
And why is that data useful? What does that tell you?
well, it tells them, or it tells the drill how to operate, when to stop, when to proceed. If it gets very hot, you might want to stop and let it cool down. One reason might be planetary protection. We don't want to create an environment, if we're drilling in things like ice, for example, we don't want to create an environment where microbes, especially microbes we bring with us, might grow. Planetary protection. But we also can learn about what's the consistency and the strength of the materials we're drilling into. So it's information that is good for the science, but it's information that is good for the health of the drill.
All right. So this you would attach onto a rover or a lander.
Yeah.
Right.
Yeah.
Okay.
Whatever vehicle's taking the drill to the places we want to drill in.
And that's something you test
Yes.
on Earth, right?
We do. Yeah.
Right. So right now, I believe.
Yeah, in fact.
In fact, right now.
As we speak.
Right now.
Right now?
Yep.
Yeah, we've got a team of scientists down in the Atacama Desert in Chile, and they're testing of this drill in an actual simulated environment.
This minute they should be drilling a hole.
This very
Yeah.
minute.
Yeah.
If they're not,
yes.
Alfonso is going to be upset.
We got some
have some
video,
footage,
some great footage we
from-
brought. We
from
got sent back to us here at Ames from the Atacama.
Yes.
Yeah, so this is the drill site, and
That's
so
from a few days ago, I think.
yeah, and that's where the scientists are set up and that's our workhorse robot K-Rex-2 mounted with the
K-Rex.
K-Rex-2.
It's our Ames rover. Yeah.
And there you can see the drill, and the blue structure is the arm that we use to collect sample and deliver to the instruments.
Nice.
And it's digging.
Yeah, you see the drill turning. Yeah, yeah.
That gear right there is where the sample comes out of the drill when it pulls back up, and the bucket is the cup. And here is one of our researchers just observing and taking notes on the experiment as it's running.
Look at that landscape.
Mars.
That looks a lot like the Viking picture we saw a little while ago from the surface of Mars. It's really Martian.
Mars on Earth, yeah.
Yeah. So cool.
What is it? Yeah, tell us a little bit more what it's like to be there, because you guys have been there yourselves, right?
Yeah. So that's the reason the drill is there and the rover and the scientist. This is part of a project called AREDS. It's the Atacama Rover Astrobiology Drilling Studies.
Yes.
A mouthful.
That's quite a mouthful. And the goal of the rover of the project is to precisely learn Mars science on Earth. So go to the driest place on the planet. That's the Atacama Desert in northern Chile. It's the driest place on Earth. It's what we call in astrobiology, in planetary sciences, an analog environment.
Analog, okay.
Analog that is
Yeah.
similar, not exactly the same, but very similar to places out there and other planets. And so it allows us to do science and test engineering without going to those places before we go to those places.
Right. Getting
Make sure
ready
that
to
it
go to
work-
those places,
Yeah, when
right.
it comes to engineering, make sure that things work properly in environments that are similar to the places we want to go. When it comes to science, it allows us to understand things like what happens if you add chicken soup to soil that is very dry. Then when we go to Mars and do the experiment, we can kind of predict what might happen.
Right.
And so that's what AREDS is doing. It's preparing NASA to search for life on other planets by going to the Atacama Desert and testing this instrumentation.
That's so cool. I love these projects.
But as dry as the Atacama is, we still find life there.
We do. This is the Earth. It's hard not to find life. And so it's a place where we can test how good or bad our instruments are. It's definitely a place where if you don't find anything, maybe you don't have the right instrument.
Okay.
Because we would expect life on Mars if it was present, or fossilized life on Mars to be a lot less abundant than even the Atacama Desert.
Yeah.
It's a lot worse of an environment.
Yeah. 'Cause you said Mars is 1,000 times drier even than the Atacama, the driest place on Earth,
Take
right?
the Atacama, the driest place on Earth, where you've been there.
I have.
Sunscreen, sunglasses, a
I
hat, and plenty
confirm.
of water.
It is
Yes, it's
dry.
really, really dry. It's so dry that no plants or animals survive.
There's
the only forms of
nothing.
life that survive in the driest parts of the Atacama are microorganisms, and they're not doing very well for that matter. And so, but then take Mars, and everything we know about it tells us it's 100 to 1,000 times drier than the Atacama.
So the idea is if you can't find it in the Atacama, you
can find
don't
it
stand a chance on Mars.
On Mars, yeah.
Okay.
If you find it in the Atacama, you might still not be able to find it on Mars because it's so much more extreme. But the Atacama gives you that confidence that if you find it there, maybe you're on the right track to find it on Mars.
So this is kind of like a test case for Mars in a certain
Test
sense.
case, yeah.
I like to call it a dry run in the driest desert on Earth.
No pun intended.
Very much intended, but it's okay. Yes.
Yeah.
But fascinating. So, yes, I did get to go last year to cover the story.
Yep.
And there were lots of scientists there last year working in the field. But this year, what's different is a whole bunch of you are here.
Yes,
this
that's
year,
right. So this is the fourth year of the project. It's the fourth time, I think, the team goes to the Atacama. In the previous years, it's been a lot of science on the ground. And testing different pieces by themselves or integrated into the rover.
You're taking soil samples.
Analyzing it. So we're doing a lot of things. But this year is special because what we're doing this year is simulate a Mars mission. And so we have boots on the ground with the rover and the drill and the instruments. And then we have a backroom science team here at Ames directing the rover what to do, receiving data from the rover, and based on that data, giving the next steps, instructions on what to do next, just the way you would do it on a Mars mission.
Yeah.
And that
So
way
you would have a team of scientists back on Earth.
Every morning,
Trying
9
to-
a.m. this
yeah.
week, we meet, we get the data that the rover collected the previous day and the instruments. We analyze that data. It's not processed data, it's quick looks that we call, which
Okay.
tell us, yeah, you got the sample, you got the data, looks good, move on. And based on what we learned, the few snippets we get from those data sets, we decide, well, go there and get that sample or go deeper and get another sample. It's a tactical decision that we need to make on the fly, pretty
I
much.
see. You call it dirt to data, right?
Dirt to data,
All
yes.
that's happening on the rover.
Thanks to intelligent rovers that we can tell them, pick that up, and the next thing we know is the composition.
Thanks, Michael.
No problem.
Cool. Right, but no, I love that term because it makes it really clear that the rover is drilling. It's pulling up dirt. It's taking the sample, throwing it into the instruments it carries.
It's doing all those
Yeah.
things. And then the instruments are processing the sample, analyzing the sample, and sending the data. And humans are not in the loop.
Yeah.
Wow.
That's so exciting.
Airplane Man 1997 says, that's cool.
He likes
I think
to
we can
drill.
all agree on that. Yeah.
Absolutely. Yeah. Here's a question also about the drill. MGM PhD asks, what material is it made of?
This is steel?
Still,
Yeah.
yep. And it's probably something like this that we would send.
Yeah.
Yes. All right. Quick.
Trap Ping Vin asks, how much analysis can be done directly on Mars compared to how much can be done by bringing samples back to Earth?
So that's a good question. There are two different levels of analysis. You might want to do a preliminary, very quick analysis to check the health of the instruments, or to make sure that you got data. Yes, no, and that has very little science involved. But then that data gets transferred, sent to us, and then we have all the time in the world to look at it carefully and analyze the details. Obviously, we might want to make decisions quickly for the next steps for the mission, but all the data gets saved in a repository that scientists pretty much around the world can access and analyze and look and tease out over many years. So we're still looking at Viking data.
Oh, wow.
And so, the science can move. It moves a very hectic pace at the beginning in the mission, but then we have all the time in the world to actually dig through the data and understand what's going on.
We do have a mission where they're looking at caching samples, right, for bringing back.
That's
right?
right. Yeah, the next one, Mars 2020.
Yeah. And that's sort of the follow-on from Curiosity, and it's going to a lake bed, right?
It's going to another lake. Yeah, what we think was a lake based on what we know from orbit. Yeah, and it's going to be the first step in a campaign for sample return to bring samples actually back to Earth.
Wow,
Very exciting.
Yeah.
Dr. Riot asks, any plans in the future to take samples from the areas where we see seasonal brine flow on cliff faces? So that's someone who's been following the Mars news.
Yeah.
So that salty water was found flowing. Right?
There are intriguing observations on the surface of Mars. We're still trying to figure out what the cause for these patterns is. But there is one possibility: there is liquid water or salty water, and so that would be like for astrobiologists, that would be a beacon. Come here and take me, sample me. But it's not easy. There are many places we would like to go, and normally the places we want to go are the most challenging ones. They're always on the slope. They're always in a difficult environment. So for whatever reason, it's never easy.
Yeah.
But this is definitely one of many places we would like to go and collect samples. Yeah.
So, okay, the challenges of drilling off-world makes me think of plans for the Artemis program. So NASA is heading to the moon
We are,
in 2024, and I think that's going to be part of it, isn't it?
It is, yeah. And Artemis is the trip back to the moon where we're sending the first woman, and then more men to the moon, presumably at some point. And so if that's setting up to be long-term habitation on the moon, and one of the things we need to do is try and get resources there, right? So we've recently found out that there is water on the moon, which is kind of surprising.
There is frozen ice crystals, right?
Yeah.
Yeah.
That's hard to extract. It's an icy material, right? And again, you will want a smart drill to try and be mitigating the risks of drilling into these icy surfaces. So stuff like we're doing on ARIDS actually feeds into the Artemis mission, which is really kind of cool.
That is exciting. Right.
So it's a multi-purpose drill potentially for many
Sounds like it.
locations off-world.
Yes, yeah.
Yeah, I like that. You've got, the scientists working with the engineers for the Mars search for life, and it's also going to be really helpful when we get to the moon.
Yeah, it's an example of how exploration drives exploration drives
Right.
exploration. It's
Yeah.
and a wheel that doesn't stop turning.
Yeah.
It's pretty cool.
So cool. Love these things.
Here's a question I like from Airplane Man 1997. What would the drill sound like on Mars?
That's cool.
That's a great question. The atmosphere is a lot thinner.
Yeah.
So it would certainly be quieter.
What does it sound like in the Atacama? Does it have a sound?
Yeah. It would sound. What does it sound like in
Sounds
the
like
Atacama?
a
You can-
jackhammer.
Yeah, when it's hammering.
Slightly higher pitched
Is it
jackhammer.
really?
That's what it sounds
Okay.
like when you're sleeping, trying to sleep in the tent in the Atacama, and the engineers are
Yeah.
testing the drill. That's what you've.
Also, if it's drilling into something hard, there's a high pitched squeaking noise. It
Yep.
could
Yeah.
it's
I remember the
Yeah,
squeaking
it's
noise.
Definitely not white noise.
No.
No, but no idea how it would sound on Mars?
Quieter, maybe
Muffled,
higher
yeah.
pitch?
Yeah,
maybe?
or lower. I don't know.
Or-
Actually, it's a good question. I don't know, but it wouldn't be quite as annoying. Actually.
Yeah.
And there wouldn't be anybody there to have to listen to it.
Yeah,
At least
yeah.
anytime
Nobody's
soon.
Not
sleeping
yet,
in the
yeah.
tent.
Not yet.
Yeah, not yet.
Yeah.
Unless
Also,
there is life on Mars.
Unless we can ask
true.
them once we find them.
we arrive and we're the worst neighbors
What do you think of
ever
the
as soon
drill
as
we
we get
sent
there.
and the noise we made?
Right?
Yeah, exactly.
Also about the Martian environment, Lejour's Pro asks, is Martian gravity similar to what we have on our planet?
No.
Right.
It's about a third, I believe.
Yeah.
And so
Does that affect the drill and how you have to design it?
That's a good question. So when we're drilling, we apply force.
Yeah. And gravity helps.
Yeah, it does. And actually, that would, I guess, affect the rate that we could extract material from the hole.
Yeah. So to compensate for some of the weight loss
Yeah.
that you get on Mars,
Yeah.
yay, if you wanted to
Yay!
die, to compensate for some that, we actually have to add some weight on the drill so that it can push
Okay.
downwards
With enough force.
with enough force to
Yeah.
go through layers. Yeah,
I see.
so it has an effect.
Yeah.
All right. More questions.
Regal 16 asks, does the drill go straight down, or does it have the ability to change directions or even go horizontally?
Straight down.
It's a straight one way.
Yes, yeah, at least
Okay.
in the setup that we're doing in ARIDS. You could conceivably try and do slant drilling, but that would be a more complicated problem again.
And risky.
Yeah, because it could, go off to one side or something if it
Or even snap
Yeah.
if you force it too much. Yeah.
Yeah.
It's made to go straight down.
Straight down. Okay. Space TV Internet wants to know if both of our guests, you guys, could be on the surface of Mars tomorrow, what would be the first thing you would do to search for life? Start digging, bring some chicken soup.
That's a good question. Well, I have, as we mentioned earlier, the surface of Mars is very different. Depending
it's
where you go, it's a very different
Buried
environment.
all over the surface, yeah.
And so if I was at some places, like near the polar caps, I would get some of that water ice, melt it, cup of tea maybe, and then put it under the microscope and see if something swims around.
Okay.
If I was in a place like where Curiosity is, ancient rocks that formed in the lake bed 3 billion years ago, I might get some samples and run them through very sensitive instruments that can analyze the chemistry and search for those traces of dead microbes maybe. If I could bring Michael with me and he could drill 2 kilometers, I would just wait on the surface until we get the sample
Yeah.
and then see what's there, if something is actually lurking down there. So depends on where you are.
Yeah, it's a well, certainly was a varied environment. It still is a varied environment from a geological perspective. So it's just like not one place isn't enough if we want to increase our odds of finding life.
I
Go
see.
all over.
Yeah.
Cubameister09 asks, how long would it take from discovering to confirming to publishing that life has been found?
Yeah.
Scientific process.
The scientific
Good
process.
Kind of like, what would it take for you to be sure?
Well,
and
I guess it depends on what you find. If you find something waving back at you, don't even publish. Just put it up on the web and let everybody enjoy it.
Would they believe you?
Would they believe you? That's a different story. If we find, it's not going to be probably such clear cut. It's not going to be a straight path. It'd be surprising. Science rarely works that way, that you have a clear path from discovery to publication to acceptance. And especially with things so important and groundbreaking as finding life on another planet. So it's going to take a while to process the data. I wish it was clear cut, but if not, then there will be debates. There will be meetings and conferences where people will go and have a back and forth. Eventually, papers will be published, and then the scientific method demands that we don't stop there. We try again, we continue, and we confirm or disprove those results. And it's that process of building on results and testing and new hypotheses and new experiments, what in the end either provides the evidence that we need or not. So,
And so, like with Viking, it took about 40 years.
Yes.
So
For example.
And not everybody's, and there might be people out there that were not convinced of the perchlorate explanation.
Okay.
And it's a valid thing in science that you can always doubt, you should always doubt the standing explanation. So
And keep testing
And keep testing,
searching
yeah.
and all that, yeah.
You can't prove things right, you can only prove them wrong.
right, exactly, yep.
All right, good one. Quick question from Digital Donger. Will Mars 2020 rover have any instruments for life detection?
It does, in a sense, because 2020 relies a lot on on doing a lot of the science when the samples come back to Earth. The focus is on smart instruments that can identify the right samples to bring back.
Ah, okay.
And so that doesn't require really analyzing every element in that rock to know exactly where it came from. We can do that back on Earth when the samples come back. But we do need instruments that can tell, well, between those two samples, this looks like a better sample to cache and preserve and bring back
Okay.
to Earth because of its composition. It might be different and things like this. So those instruments are selected precisely to do that. Select the best possible samples for return.
Okay, neat. All right.
Sleepy_Gary asks, were you inspired by any sci-fi to pursue this field?
No.
Yes.
Scientist, space scientist, sci-fi. No. I'm a Star Wars fan.
You are?
Yeah.
iRobot by Asimov. Yeah.
Really? Yeah.
Yeah. Oh, and Star Trek, obviously.
It
Yeah,
always has to
obviously.
start somewhere, right? With the imagination.
Yes.
Yeah.
We've had endless debates about what's the best science movie, sci-fi movie
Yeah.
in the Atacama, Michael and I.
Got a lot of time on your hands there.
You
Or-
get
Oh, yeah.
you get plenty of time. Yeah.
And no internet, so...
And no internet. Oh my God, yeah.
We don't have a lot of time left, so maybe one more question from MGM PhD. What have we learned about Martian dust or dirt that would impact robotic tasks? Is that something you're learning from the ARADS project in the Atacama? How does
we're
a
actually
rover
having...
deal with the dirt?
We're actually having an interesting problem in ARADS right now, in that when we're drilling up dirt, we have a camera that's looking at where the dirt comes out and goes into the scoop, and the dirt is all getting stuck to the lens of the camera, which is a problem for cameras, because they need to be able to see to be useful. Yeah. So that's that kind of that mitigation, dust mitigation, is a big thing.
That's a problem. Wind is a problem. Do you remember we have this scoop that is collecting cuttings from the drill and then brings them to the instrument? If you have strong winds, your cuttings might blow out of the scoop. So we learn how to position the scoop and the rover in a way that it blocks the wind and prevents sample loss.
Okay.
Yeah, we learn a lot of things.
Nice.
All right, keep going, ARADS. We need
Yeah.
to know these things before our rovers go to Mars and start drilling. But that is all the time we have for today. It goes so
All right.
quickly. But thank you so much to you guys for
Yeah,
joining us today.
thank
This has
you.
been fascinating. And thank you to everyone who joined us in the chat on Twitch. Join us next time. That'll be October 24th for our second annual NASA-themed Halloween costume and cosplay contest. So that was a lot of fun last year. Join us for that. Thanks for watching, and we will see you next time.